First of all, let me start by thanking the organizers for giving me the opportunity to speak at this very nice conference. The title of my talk is Fluxbrane inflation, and it's based on work done in collaboration with Arthur Hebecker, Dieter Lüss, Stefan Steinfurt, Timo Weigand, and Moritz Künzler. So just as a very brief motivation, as you all know, inflation is one of the crucial concepts in modern cosmology. And obviously, it's a huge area of research. However, for this talk, I will simply content myself with the perspective that, from a particle physics point of view, the challenge is to identify a scalar field in your theory which has a potential which is flat, essentially. Okay, and the flatness of the potential is measured by the famous slow roll parameters epsilon and eta. Okay, and there have been many attempts to construct models of inflation in string theory, some of which have already been discussed at this very conference. In my talk, I will present you a specific example of a general class of models, of inflationary models, which go under the name brane inflation. And the idea here is to identify the four-dimensional inflaton with a modulus which parameterizes the deformation of two d-branes. And famous examples for these class of models include, first of all, the brane-antibrane proposal by these authors, and also the D3, D7 inflation proposal, where supersymmetry is broken by a flux, a non-supersymmetric flux on the D7 brane. And there are several more. However, I mentioned these two because our proposal turns out to be actually somewhat close, especially to the D3, D7 proposal. However, in these models, if you compute the potential and compute your slow roll parameters epsilon and eta, you find that quite generically you're facing an eta problem here. Because, for example, in the brane-antibrane inflation proposal, you find that if you compute eta, it involves this ratio L over R, where L is some kind of typical length scale of your Calabi-Yau manifold, and R is the brane separation. So obviously this ratio is typically much larger or larger than 1, giving you this eta problem. Okay, and this has been known for a while, and there have been some proposals for how to circumvent this problem. For example, you can consider warp compactifications, or you can consider very anisotropic compact spaces. However, in this talk, I will present you a different idea, which goes under the name Fluxbrane inflation. I will first review some aspects of this model and then talk about modular stabilization, which is obviously crucial in these models, before I then conclude. Okay, the idea of Fluxbrane inflation is pretty easy to state. The idea is to identify the four-dimensional inflaton with the relative deformation modulus of two D7 branes. So it's D7 branes which we consider, and these carry some supersymmetry breaking flux, so that at one loop level a potential for the inflaton is introduced. Okay, and now you can in the setup you now can compute your inflationary potential, and you find that it can be written in this reasonably nice form. I will just simply walk you a little bit through that. G-Young-Mills is the gauge coupling of the gauge theory which lives on the D7 brane pair. Xi is a D term which appears in the low energy effective action because you turned on some flux on the D7 branes. And phi is obviously the four-dimensional inflaton, and alpha is a quantity which, for the purpose of this talk, you can basically think of as measuring the induced D3 brane charge by the D3 brane charge which is induced by the flux. It's actually crucial that there's the second term, but I won't have to discuss this. I won't have time to discuss this in more detail. So, and just as a comment, if you put alpha equal to 1, this is simply the ordinary potential of ordinary D-term hybrid inflation, which some of you might know. So you can think of this as being a specific type of stringy realization of D-term hybrid inflation, basically. Okay. So now with this potential, you can now go ahead and compute the slow roll parameter eta, and this time indeed if you are at large volume, i.e. L is reasonably large, you find that eta is naturally much smaller than 1, so you don't have this eta problem which I talked about before. The spectral index turns out to be in agreement with WMAP7, with the WMAP7 data at 2 sigma. And finally, if you consider just for simplicity, a manifold which is roughly isotropic, you can actually compute, or you get out that for producing the right amount of curvature perturbations, you need a manifold which has a size of roughly 10 to the 6. So this fits well with what I told you here, that we need large volume in order for eta to be reasonably small. Okay, and furthermore, I mean for a volume which is 10 to the 6, it's obviously that we should be discussing modular stabilization in terms of the famous large volume models, because there we can actually get volumes which are this large. Okay, so there have been quite some talks already about large volume models at this conference, so I will be quick. I mean, the most simple thing you can do is consider just a manifold which has 2 Kähler moduli. One is associated with a large force cycle and one is associated with a small force cycle. And in this setup, stabilization in terms of these large volume models happens through an interplay between alpha prime corrections to the Kähler potential and non-perturbative corrections associated with the small force cycle to the superpotential. And you can now, from these two effects, compute the leading order F-term potential, and after this expression is actually in this expression the small force cycle volume is actually already integrated out, and you find that concerning the overall volume, this gives rise to an ADS minimum in which this volume is stabilized at the bottom here at the minimum. Okay. So the minimum is ADS, so for inflation to work, we obviously have to lift it to the zeta somehow, and in our setup it's most naturally done via the D term because we have it anyways, basically. So, however, the D term scales like 1 over the overall volume squared, so we have a problem here, because naturally, if you consider just the volume scaling, the D term is much larger than the F term actually. Okay, so naively, if you add a D term, which we have in our inflationary model, this will simply lead to a washout of the minimum, and it will lead to decompactification. So one idea is to consider consider warping, namely to put the flux in a region of your Calabi-Yau which is highly warped, in order to lower the energy density which is induced by this D term. However, in our setup, it seems more appropriate to go another way, namely to enhance the size of the F terms. And this can be done, for example, by considering very large values of your tree-level superpotential W0. So naively, I mean, what would you expect? Naively, you would expect that you need W0 squared like volume, has a size like the overall volume, basically, so that the scaling of these two terms is pretty much the same. Okay, and this is fine, but there are actually problems associated with a W0 which is so large. In fact, it turns out that for a volume which is 10 to the 6, you are not able anymore to satisfy the D3 tadpole constraint. Furthermore, parametrically, your gravitino mass is larger actually than the Kaluza-Klein scale, which is bad for your supergravity approximation. And there's also a problem which I won't discuss in detail, just for those of you who know. There's a problem that the cosmic strings which are produced at the end of brane inflation have an energy density which is actually too large to be compatible with current experiments. Okay, all of this points towards, or all of this suggests that we should consider an anisotropic model where we have more freedom to accommodate the data, basically. Okay, and in our recent work, we considered a model which has 3 Kähler moduli, 2 of which are associated with large 4 cycles or 2 cycles respectively, and again 1 which is diagonal and which is associated with a small 4 cycle. And there's now obviously an additional degree of freedom in the theory, which we can choose to parameterize the relative size of the 2 4 cycles or 2 cycles, as you wish. And this ratio, the interesting thing now is the way in which this ratio appears in the leading order F-term potential, not leading order, but in the relevant part of your F-term potential and the D-term potential. Namely, if you consider the D-term potential at large x, the D-term is actually suppressed by 1 over x. So it, if you are in the regime where x is large, the D-term energy is actually lowered by this effect, whereas the F terms are enhanced by x squared. So, and the F terms is in the F terms, the W naught shows up, which previously had to be very large. So now we can think of a kind of combination, making this term large by a combination of a reasonably large W naught and a large x squared. Okay, and furthermore, the D term in this regime where x is large is actually smaller than in the isotropic case. So this is nice because this is precisely the direction which we need. W naught can be smaller in this anisotropic case, and it can be small enough for the discrete tadpole constraint to be satisfied. Actually, so the discrete tadpole constraint can be satisfied. We don't have the problem that the gravitational mass is too big anymore, and also it turns out that this is precisely the direction in which we have to go in order to lower the energy density of our cosmic strings so that the bound is actually satisfied. Okay, this is basically the outcome. So let me conclude. I presented you Fluxbrane inflation as a model of, or a specific type of stringy realization of D-term hybrid inflation, which has attractive phenomenology. Namely, we can consider moduli stabilization in terms of the large volume models. The spectral index turns out to be about right, and furthermore, we have a mechanism to suppress cosmic strings. We have a kind of toy model, which I described before, in which actually all Kähler moduli can be stabilized in the context of these large volume scenarios, and furthermore, it is actually possible to have an uplift via a D term. Okay, and the next step is obviously to consider or to investigate higher order inflaton mass corrections, but this is very much work in progress, and due to the lack of time, I won't have enough time to discuss this in detail. So I guess I just finish. Okay.
Questions? So what is your gravitational mass?
Well, it's basically in units of M Planck, it's W naught over the overall volume. For in the isotropic case, it's basically 10 to the minus 3 in units of M Planck, basically. So we have high scale SUSY breaking, obviously.
That was the anisotropic or the isotropic?
Isotropic. In the anisotropic case, actually I don't have the number in my mind. It's a bit lower. I'm not sure what the exact number is. I can give you the number later. But it's not hierarchically smaller. It's still high scale SUSY breaking.
More questions?
Anyone? Okay, let's take the square again.